Hello guys, in this video we will implement the function which finds all the connected components in a graph. Okay, in the previous video we already implemented the disjoint set data structure and function which check the cycle in a graph. And today we will use the disjoint set data structure to implement the finding connection component function. And let's start with the type signature. I will call my function connection components, and it takes some graph of type A on input. Of course, I need this constraint and for all here. And what we return? I want to return my connection component as a mapping. There the key represent the representer of the component, and the value of the mapping represent the list of all the vertices which contains in that component. So I can define this type like mapping from A to list of A's. Okay. And now let's write the implementation. On input we will receive some graph which can be unpattern match. Unpattern match as the graph contains a list, so I will show you the definition of the type of the graph. So graph is actually a list which contain all the edges. The edges is the pairs of the vertices. Okay, and we have it on input. Okay, how can I find all the connection components? Actually, I will find them in this way. I will take all the vertices of the graph. Then for every of these vertices, I will find the representer of this vertex. Of course, at first I will construct the disjoint set data structure for all the edges in this graph. So I will call the union function for the edges, and I will collect this information into the disjoint set which contains all the information about connections. Okay, when I take every vertex of all the vertices of the graph and build a representer of this vertex, okay, and then I will build the key and values. At first we will be in the list, so the keys will be representers and the values will be the actual vertices. And then we will use the special function which presents in the data map module. It can construct a mapping from a list of pairs, and it takes the first element of a pair as a key and the second in the value, and also it can somehow merge these values with the same key with some function. Okay, later I will show this function, but now let's start with the implementation. Okay, what I needed first? At first I need to construct a list of some, the list will be contain some pairs where we have some keys and values. Okay, values. First we take all the vertices of the graph. We have the vertices function. We pass the graph into it and it produces to us vertices. we can look at every vertex of this list of vertices, and then as a key, as I said, they need to find the representer of this vertex. And they can do this with the find function of our disjoint set data structure. This data structure has this interface, and it has a find function which takes some disjoint container, some vertex, and maybe return the representer if this vertex represents present in our container. And also the second number here is the number of nodes in this component. Actually, we don't need this number. We only need this function to detect the representer of the component. Okay. And this means that I need to run, use this function here and provide vertex for it and disjoint set data structure. This data structure I define a little bit later, and this result will be the key. The representer will be the key, and as you see, I use it as a first element of this pair. And now I need, of course, because there is a maybe type where in the end they need to extract the just value from it. I assume that all our vertices presented in our disjoint set, I will construct it in that way that all the vertices present in there. So I am extracting them from just function, and I take the first element, okay? Because the first element represent me the representer vertex, and the second is the number of the elements in the connection component. You can see again, I will show you this type. It is here. So, and now I need to define the value of this key to value mapping, and the value will be the list which contain this vertex. Why this is a list, you will understand a little bit later. Now it is important that we construct the pairs here from some representer k to the actual value. And we will construct these pairs for all the vertices. And actually we done this using this expression. Now, having this, actually I can construct my mapping. So the mapping, there is one instance function. I will show you this type signature. So I will import, and let's look at its type signature. This function called from list with. Sorry, from list with, like this. And you can see that it's take as a first parameter it's take some function, as a second parameter it's take the list of pairs. They have some k and value of type A. And of course it is possible that in this list will contain some pairs with the same k. And how can we build the mapping from the pairs to the same k? Of course, we need to provide this somehow function which merge the values with the same k. And actually this function do this for us. And this means that we can use this function here to construct our final mapping. Okay, and of course for merging we will use the plus function, the concatenation list function, because we construct the list here for values, and to merge them we need to concatenate them. Okay, Now, to do the last step, I think they need to do the definitions. We need to do the definition of our disjoint set name and actually, yes, we only need to define our disjoint set. What the type it has? Let's it has the type this type. This type implements the interface, the disjoint set type class of the abstract data type of disjoint set, and we use this type here to represent our disjoint set, and that's why we will set this type as type of disjoint set of some vertex A. Now I need to construct my disjoint set. How can I construct it? Actually, this is very simple. I can use fold L function for this, and I need to start from some initial disjoint set that all the vertices contains, and then I need to pick up all the edges, and for every edge I need to run the union function again and again. So I need to do somehow folding. And using this we can write the implementation. So our disjoint set actually is constructed with fold L function, which use some function for merging, use some initial disjoint set data structure, and they need to provide the list of edges. Actually, this is this list. Which and pattern match from our graph. It contains the list of all the edges. And of course we need to define the f merging function here, and we need to define the initial disjoint set data structure. As I said, at first we initialize our disjoint set with vertices, actually we have this function, helper function here, which takes some list, this function. It takes some list, and using folding, use making set for this vertex, every vertex. Initially start with the empty disjoint. So this from this function will construct to us, if we provide the list of vertices, it will construct for us the initial disjoint set data structure. Okay, and now I need to do the merging function. This is a function, because this is a fold L function. At first it takes the initial disjoint set, and then it takes the element of the list. And we know that the element of the list actually is the H. And this means that we can unpattern match this element here. And now, so I think I don't need this brackets. And now when you unpattern match this H, we can run the dunion function, which takes some element of this disjoint set, another element. Let's take this disjoint set D and produce to us new disjoint set. There we try to connect the components to which belong A and B. Okay, and this means that we can run this function here for our A, B, and D. Okay, so we start from the vertices not connected at all, and then we folding our list using dunion function, and this means that in the end of the folding we will produce our final disjoint set data structure, which can be used here to find our representatives to every vertex. Okay, now I think we can try to compile this thing. So I will, okay, let's run this again, and I will load my file, and you can see it's loaded, it's okay. And now we can provide some graph here. We have some graph G. Okay, let's remove this H from it. So this is a graph from a previous video. It's like a square from A to B, B to C, and then from C to D, and from D to B. And let's make it like a square. Okay, now I can reload and output this graph here. You can see it. And let's run our function which detects all the connection components for this graph. And you can see now we have only one connection component with representer D, which contain D, C, B, and A. So this means that all the elements can be find the path from every element to every element in this value. So let's add some connection component. For example, what if I create here from A to some X? Okay. And what if I add another connection component from some J to K? Okay. Now we can reload and run again. And actually you can see that here is our new connection component. I will show you the graph. So this is a new connection component which they added, which had the representer K and J, and our first connection component which had the representer X now, and the elements X, D, C, B, and A. So actually this is like an equivalence relation, and this is the representers of the equivalence classes, and this is the equivalence classes. So this is they somehow do the partition of our initial set. Okay guys, I think this is all for today. Thank you for watching. Push like button, push subscribe button, write the comments if you have some questions or if you found any errors. So see you in the next video. Bye bye.